A very warm good morning to everyone. I'm happy to welcome all the participants on the seventh day of AECT sponsored 2-week FTP on cutting edge trends in deep learning approaches. So, our resource person for today's session is going to be Mr. A. Arun Prakash, Assistant Professor, Department of Electronics and Communication Engineering. He is having 10 years of teaching and research experience, and his research interest includes signal processing and deep learning algorithms for computer vision applications. He delivered guest lectures in multi-rate digital signal processing, mathematical methods in image processing, computer-aided breast cancer detection and diagnosis with deep learning algorithms, forecasting crop yield prediction using deep learning models, computer vision using Python, applications of deep learning in healthcare. I'm happy to welcome Mr. A. Arun Prakash, Professor, Department of Electronic Communication Engineering, KEC. Today, he is here with us to share his expertise in deep learning models for computer vision. Now, I hand over the session to Arun Prakash, sir. Sir, sir, Arun Prakash, sir. Arun Prakash, sir.
Ma'am, sorry, I mistakenly closed the meet.
Okay, sir. Okay, sir.
Okay.
We start, sir. We start the
Yes.
session.
Okay, ma'am. Okay. Good morning to all. So, myself Arun Prakash, and I'm working in my area of research is signal processing and deep learning. So, before starting the session, I would like to know the background knowledge of the participants. So, I'm just posting one link in the chat box. So, you just click on that link and then just answer a few questions. So, you just take a minute to answer those questions so that I can change my flow of teaching based on your knowledge.
Sir, you received response from participants, sir?
Yes, ma'am, I am receiving the responses.
Okay, sir. Okay. Sir, in this FTP session, we have already discussed about the basics of Python, sir. NumPy, MATLAB, Pandas. These topics
Okay,
we have already discussed, sir.
okay, ma'am. Okay, it's all right. Ma'am, is my screen visible? Is the presentation visible, ma'am?
Yes, sir. Visible. Getting visible.
Okay, ma'am. Thank you. Okay. Good morning again. So today we are going to look into one of the major application of deep learning algorithms. Actually, the great era, the breakthrough happened only in computer vision application. After that, this deep learning algorithm has been adapted into many different domains. So in this session and in the upcoming sessions as well, so we are going to look into the computer vision, what is computer vision and how deep learning algorithm is being applied for computer vision applications, all these things, but without look into the mathematical equations. So if you are a research scholar, say for example, I hope there are mix of participants, probably many of your faculty are willing to apply this deep learning algorithms for some application, and a few of you are research scholars willing to develop some sort of deep learning algorithms. So in such a case, uh, if you are a research scholar, it is required to have some, at least some mathematical background to, apart from coding knowledge, we should have the mathematical background of all the algorithms. But in order to understand the concepts and to develop an application, not much mathematical knowledge is required. So I'm going to keep the session simple with visual illustrations instead of mathematical equations, which may I think it's very boring if you put a mathematical equation on a slide. So many will turn off their screen. Okay. So by the way, deep learning is not a quite a new field. So it is there because of the because today in today's era there is no limit on gaining an access to data. So every day, in internet, trillions and trillions of images are being uploaded by billions of people, and then again we have much computational power. So deep learning is now a buzzword because of these, but the algorithm, the foundation for deep learning has been laid out very much earlier in 1970 as well. So if you look at today, so you need not to know much about how the deep learning architecture or how everything works. So you can just simply use uh, the existing deep learning frameworks like Keras, TensorFlow, or PyTorch. So when we talk about computer vision, usually today most of the data are actually captured in the visible spectrum, right? Your mobile phone, because everyone has a mobile phone, so they can take a picture. But that picture is actually captured from the visible spectrum of the entire electromagnetic region. But there are applications where the pictures are taken using microwaves, like in satellite, radar, and then ultrasounds. Okay, so it is not just restricted to visible region. So computer vision means, so capturing an image in other spectrum is also included in computer vision. Especially if you look into the medical image, they use an electromagnetic wave, especially oftentimes it is X-ray or ultrasound, all these things. Okay, so again we have an image captured from some modality, then we need to extract some information from this image. Okay, so this is what computer vision is all about. So here I'm just displaying a simple picture from a movie called, I think, Mangalyaan. So you can, so what are all the informations you can extract from this picture? So how, what are they doing? So if I ask a few questions, okay, say for example, list out all the objects in this picture. We can do do this without much effort, right? So we can see that there are people's, probably this must be some sort of restaurant, and there are objects like a bulb and tree, and then a person wearing a belt, and even we can see the glass tumbler, and even we can say how much it is filled, whether it is half empty or half full. So we can come up with n number of information given this a simple image. Okay, so for us this is we do all these things quite effortlessly. So we don't take much time to recognize all these things because all human beings, not only human beings, all the animals, mammals have been evolved for more than millions of years. So our brain somehow learn how to do all these things effortlessly. Okay. So if this is so easy for us, then why is it very difficult for a computer to recognize all this information? Okay, so you show an image to a computer, you ask some question, probably you will get some answer, but we don't know whether that answer is justifiable or not. So it is not going to be quite easy, even for a simple task. You show an image to a computer and ask whether it is a person or something. It is actually developing such algorithms is quite difficult. Okay, so I would like to emphasize this using a real world story. Okay, so here you can see a person called a well-reputed researcher Marvin Minsky in MIT. So in people around 1950 and 1960 thought that, so that is where that is when the concept for the computer, all these things were conceived, and they really thought that computer vision is quite easy. Okay, initially, but after taking a project and working on it, they realized that it is not that much easy as they thought. Okay, so here you can see a picture where a robot is trying to solve a different size of cubes and trying to stack one cube on the other based on their relevant size. Okay, but this problem was not solved until 2016. So I just highlight this. So they thought the problem is easy. The problem was easy. It takes not much. It may take just an year to solve this problem. But once they started solving this problem, then only they came to know that it is actually very complex than anyone imagined. Okay, so quite a surprise. These kind of problems were solved only by 2016, especially by deep learning algorithms. Okay, so you can see now, you can realize how important deep learning algorithms are. And one more thing is that it is not solving all the problems, but it is solving majority of the problems that industries have been facing for the past 10 or 20 years. Okay. And one more thing is that, suppose if my voice is not audible, or if you have any questions, you can just stop me at any point of time. Okay, so just if until you get an answer. Okay, let us move on. So then the real question is why it is so hard. So what is the obstacle? So why the computers are struggling a lot? And one thing is that our human brain is evolved to understand images and videos as quickly, but it is very hard for our human being to look at the numbers and say something about it. Okay, so we are bad at recognizing numbers and manipulating equation, all these things. Oftentimes people hate maths because it is not quite intuitive, right? So it involves a lot of equations, a lot of numbers, so we tend to hate that. But we love pictures, we love videos. Even we can see one series or an episode for one full day without getting tired, right? But if you study a maths book for even for 10 minutes, you will keep it aside. The reason is that our brain is not actually built on based on to recognize to understand the numbers quite effortlessly. We need to put a lot of effort in order to understand the mathematical concept. But the computer is just opposite. So it is actually designed for numbers. Okay, so it can only see through the numbers. So whatever we talk about, we have to instruct the computer to look into the numbers. So here is a picture. What we see is a cat, but what computer sees is a numbers. Okay, probably you may already know what is an image, all these things, right? So even though you already know about these things, let me talk about quite a little bit about that. So we always represent the image with height and width, right? And if you have three channels, I mean, if you have a color image, we will have three channels. One is red, and another one is green, and another one is blue. Suppose if I have shown you these numbers and ask you what object these numbers represents, it is not quite easy for us. We can never do that. Okay, by looking at these large numbers, we cannot say whether it is a cat or dog. But we need to instruct the computer to make a conclusion based on these numbers, right? Say for example, very simple image of size, say for example 100 cross 100. Even if it is a gray image, we will have only one channel, that is gray channel. So but how many numbers are there? So if it is an 100 by 100 image, can you tell me how many numbers are there? So it is a matrix. So if that is the case, the matrix contains how many elements? Okay, so let me answer that question. So if I have a matrix, every image, okay, computer vision, all the computer vision algorithm depends on this matrix. Okay, if you assume very simple image of size 100 cross 100, then the number of elements in this image is going to be 100 multiplied by 100, so which is 10,000. Okay, and each of these numbers, okay, so every number, so I have some grid of numbers row. So each element inside the matrix can take value between usually from 0 to 256 or 255. Okay, so the possible combination goes extremely higher. Okay, because this particular element can take value either 0 or up to 255. Similarly, the second element can take value 0 or 255. So the possible combination actually is enormously higher, right? But one particular configuration gives rise to this pattern. Okay, so as long as computers are concerned, or computer vision algorithms are concerned, they are looking for patterns. Okay, so these patterns will be based on the value of these elements. Okay, so I have 10,000 elements or 10,000 numbers. Each number can take value between 0 to 255. So the possible combination goes 2 to the power 2, I think, not just 10,000, it is beyond that. Okay, because each of them are taking 255, so it is 2 to the power 255 power 10,000. Okay, so it is quite enormously higher. So I have to deal with these numbers. I mean, when I say I have to, it is actually the computer has to deal with these 10,000 numbers somehow. Okay, so I have to pass all these 10,000 number to the computer algorithm. Okay, then algorithm has to look into all these 10,000 number, and then based on that it has to make a judgment, or it has to extract some information. Okay, so whether it is cat or dog. So seemingly it is quite harder problem. Okay, and usually here I just display an image for 0.5 seconds. Okay, and within this 0.5 seconds, even though you have just looked into this picture for 0.5 seconds, your brain have gathered majority of the information about that particular picture. Maybe you might have observed there is a lady in the picture, there are bunch of bananas, even a child, probably girl child. Okay, so all these things. So the question is how long it takes for a brain to process a given image. Okay, so the study has shown that it takes around some 550 milliseconds to 850 millisecond. Okay, so even if it is a static image, it is very less than that. It also depends on the number of objects in an image. All these factors are there, but usually it is from 550 to 850 milliseconds. Okay, so but today, even with the GPUs, today we have an access to GPUs. Especially if you look into Google and Facebook, the tech giants, they have an highly supercomputers like that. Okay, but still they are struggling to develop an algorithm that can take decisions quite fastly as like our brain does. Okay, so which means our brain is superior to all the deep learning algorithms today we have. Okay, so it is not even closer to 1% of what we do quite easily. So which means there is a potential for lot or scope for lot of research. So this is how brain. So this is just an idea how a brain process an image. So usually retina is like our camera. So all these things are captured in the retina. Even retina carries out some sort of processing in itself. Okay, like we have a mobile camera, but camera doesn't do any processing, right? It simply acquires the light and then it simply converts that into a digital image and the processor stores it. But our retina, even though it is said to be a kind of um, camera, it still have some processing unit inbuilt with it, and then that information actually passes through various subcomponents in the brain. Okay, so here we have shown only a few subcomponents, and each of them are dedicated for a particular task. Okay, so probably each of them look for an edges in an image, and then they can interact with all others. Unlike our deep learning algorithm, as you can see from here, there are many components. They are not isolated. Okay, say suppose this particular area looks for the orientation information in a visual input, and they also communicate with the all other subcomponents. Okay, in order to make a conclusion about that. So how do people know this is the area actually looking for orientation? Suppose if there is any damage to this particular area, people will have a difficulty in learning the orientation. Okay, especially learning the whether it's a horizontal line or a vertical line. Okay, so this is how people, I mean, the neuroscientists came to know how which particular area of the brain is responsible for which task. But this is a highly simplified version. Okay, and one important thing is that it is not just for the human brain, so it holds true for any sort of brain, even the very simplest animal like cat or mouse. Okay, so computer vision is not an isolated domain, so it requires a knowledge from all other domains. So as you can see from this picture, what we are actually talking about is machine learning. Okay, so if you are a machine learning engineer, you can contribute to the contribute or you can solve problems in computer vision engineering, and also you can see image processing and then signal processing, information theory, okay, and then computer science, even from the neuroscience, optics. All these major fields are contributing to computer vision. So it is an intersection of knowledge from all domains, almost all domains. Okay, so we cannot be good at all domains, but we can at least we can have a strong foundation in at least one or two domains, right? So if you are good at machine learning, if you are good at image processing, then you can contribute to problems in, I mean, you can solve problems in computer visions. Okay, so usually uh, the computer vision okay, so let me give you the definition for computer vision, but this is not an exact definition, so it is a kind of just as a guideline. Okay, suppose if you ask us to define what is computer vision, this particular definition is most suitable. Okay, so you can see it is a scientific field. It's not an engineering field where only we focus on an application, but it is a scientific field. Okay, so that extract information out of digital image. So very simple but beautiful definition, right? So you are given with some image, natural image, it could be anything. Say for example, if I consider natural images, this image is composed of many objects, right? So how many real world objects are there? So if you keep on counting the number of real world objects existing, at least that is known to us in your day-to-day life, probably table, box, all these things, right? Book. So everything is a different object. So if you list it out, there are 10,000 different objects are there in the real world. Okay, which means each image may contain a subset of objects from this 10,000. Okay, so if you really want to develop a good computer vision application, okay, like if you want to really want to import a capability of a human brain to the computer, The computer vision, that particular algorithm must recognize all these 10,000 objects. Okay, then only we can say it is on par with the human being in the computer vision task. Okay, so but it is not quite easy, as we can learn later. It is not going to be much easier. Okay, it is going to be extremely difficult even with the help of deep learning algorithms. Okay, sometimes you can also use some other definitions like if you are from computer science background, you can say it is building algorithms, okay, that can understand the content in an image. Content means again information. Okay, so what are all these problems? Or if you ask me to list out what are all the branches of computer vision? Computer vision is just it is a huge branch in itself. Okay, you can study, even you can offer this as some sort of undergraduate course, because it is a really big field. So so I'm talking about before 2012. Okay, so usually from 1980 to 2010, you can see the one part of the computer vision is feature extraction or feature engineering. Sometimes they call this as feature engineering. Okay, so there are researchers who put their effort to learn new features. Okay, these things are still remains even in the deep learning era. So there are researchers who work on developing classification and object detection algorithms. Okay, so this is each of the domains that I have listed out here is a research field. Okay, you can do research in this field, or you can develop an application in this particular field. Okay, so object detection and classification is what usually many of the researchers are contributing in this particular field. Okay, and then segmentation, yeah, if you look into the remote sensing and medical images, people even in autonomous driving vehicle, they tend to use this segmentation algorithm. Okay, so probably they will use object detection or segmentation. Okay, these two are contributing more to the computer vision. So if you count the number of people working in computer vision domain, and if you again classify them, majority of the people will work in either in an object detection or classification algorithm or segmentation algorithm. So if you move on to video, you can also use object tracking and registration, fusion, and post estimation. Everything belongs to the computer vision domain. Okay, so but these things are very specific area. Okay, so we cannot cover everything in a single session, but I am just giving you overview, and I am just showing you all these fields are there, and all of them belongs to the computer vision area. Okay, so before getting into this deep learning for computer vision, we may ask this question. So what is the problem with the traditional or conventional machine learning? Why don't I use conventional machine learning algorithms? Why should I go for deep learning algorithms? Okay, so in order to answer this question, let us take a simple example. Okay, so here you can see there are some words: sensory, brain, visual perception, all these things. So just we are there are I think around some 10 to 15 words are here. So if I give you these words and ask you what kind of book these words belongs to, okay, so see, assume that you have a book which contains 1,000 pages. Okay, now it is a kind of game. I am just giving you 10 to 15 words in order to recognize what sort of book that I am having in my hand. Okay, so I am picking up only 15 words out of those from those 1,000 pages of book. Okay, so will that be sufficient? So by looking at this set of words, you can immediately recognize that this book must belongs to a field of neuroscience or biology or something like that. You will never say this book belongs to actually economics or history. Okay, this is the case, right? So I don't need all the words from the thousand pages in order to say whether this book is and belongs to a neuroscience field or an economic or a history field. So again, if I have other set of 15 words, okay, this time a different set of 15 words, as you can see by looking at these words, you can again say whether this book belongs to neuroscience or not. So definitely it doesn't belongs to neuroscience. probably it might belongs to economics. Okay, very close categorization is this might belongs to some sort of economics, right? Because all these words are related to economics. So the key takeaway is that we don't need all the words in the book in order to recognize whether this book is in order to categorize the type of the book, right? Like this, I have an image, even though the image size is 100 cross 100, right, which contains, as I told, it contains 10,000 numbers. So I don't, suppose, let us say this image is contains some objects, probably some sort of cat or dog. Okay, uh, these are all pixels, so I have 10,000 numbers. Okay, so which is actually coming from this entire image. I don't need all these 10,000 numbers in order to say what object this what is this object, right? So whether it is a cat or dog. So what we do is usually we may look at a particular region. Okay, we compute something and then I just pass these three regions. Okay, so probably let us say I map these 10,000 numbers, okay, to some, say for example 50 numbers. Okay, which means I take a description from these 10,000 numbers and I only keep the vital component. So it is now 50. So I use these 50 numbers to say whether this particular image contains a cat or dog. Okay. So this, what we call it as a future engineering. So in a conventional ML, I have an image, and when it is a color image, we will have three channels. And if the dimension is 100 cross 100, then totally it contains 10,000 elements, and for each channel it is 3 into 10,000. So totally I have 30,000, correct, 3,000, 30,000 numbers, right? What is 30,000 numbers? Each number represents the pixel value. Okay, so instead of using all those 30,000 numbers as it is, okay, so what we do is we try to identify regions, very important regions in a picture. Say for example, here it is highlighted by some oval shape, right? So these regions are identified as important regions. So we encode these regions, okay, we take these regions and then we encode it into different numbers. Okay, so that number we call it as an code book or a vector, okay, or future. Okay, so this 30,000 numbers are now encoded into, say for example, 600 numbers. Okay, so we are just playing with numbers. So these 30,000 numbers now encoded, remember it is encoding is a different word, so encoded into 600 numbers, then this sort of encoding is called as future description and future engineering. Okay, so which means there must be some people, it depends on different applications. Say for example, if I am working in optical character recognition, I need a different future engineer. If somebody is working in medical segmentation, they need a different future engineer. Okay, so developing a particular feature deduction or feature description requires a future engineer who should be specialized in feature engineering domain. Okay, so this was the case before 2011 or 2010, something like that. Okay, suppose if you are already working in some sort of computer vision applications, probably you might have heard shift feature, which is the most commonly used feature, and hop feature. Okay, so all of them are future descriptors. Okay, I will choose a particular region and then I will extract these features and then we convert that into a vector and then we simply stack it. Okay, so after this future engineering, what we do is now I have these 600 numbers extracted for each images, then we will use some sort of classification algorithm. Okay, and these 600 numbers, say for example, if I have only two numbers, let us say I have x1 and x2, I have just two numbers, so I can represent these two numbers as a point in two-dimensional coordinate, right? I have x1 and x2, then this x1 x2 must be somewhere here. Okay, like this. So like this, we have 600 numbers, say probably x1 2 x2 all the way up to x600, right? You can represent these 600 numbers as a point in 600 dimensional coordinate. Okay, so this is what illustrated here. Okay, the key takeaway is this is a vector. Every vector can be represented as a point in its respective dimension. Okay, so and then I need to build a classifier which try to distinguish these different points. Okay, the classifier, the purpose of the classifier is it will divide these grouped points. Okay, this may belongs to class 1, these points belongs to class 2, these points belongs to class 3, like this. Okay, this is how people did, or this is how people followed or solved many sort of computer vision applications before 2010. Still it is there, it doesn't mean it is absolute, but for many reasons still we didn't ignore the conventional ML algorithms, but we have to look into the drawback of this. Okay, so the question is, I hope you are able to follow this up, and if you have any questions you can ask me now.
Sir?
Hello.
No participants not having any doubts.
Yes ma'am, let them ask. I'm very happy to. So they have no doubts or they have many doubts?
No doubts, sir. I think no doubts.
Okay ma'am, it's all right. Okay.
Continue, sir.
Hello, sir.
Sir, give me a minute, please, sir. So 1 minute. Sir, ma'am, VLSI lab, first floor. Hello. I think someone have. Yes.
Yes, sir. Sir, good morning.
Sir, good morning.
Sir, we have a lot of feature extraction algorithms. So, where can we use those feature extraction algorithms in deep networks? As features are extracted automatically. Now, all these feature extraction algorithms like SIFT, SURF, RANSAC, and so on
Yes.
can contribute anything to the computer vision concepts using deep networks.
Yes, sir. So today we don't use those sort of features for simple applications, say for example classification, all these things. This was there before 2010. Before 2010, we extract all these feature and then we pass it to the classifier. But deep learning carries out this feature extraction on its own automatically, as you said. But still it exists. Still we use feature extraction where we need a reliable output from the classifier. Say for example, if you relay, suppose if you consider an example, say for example autonomous driving vehicle, where people use deep learning algorithm, they train the deep learning algorithm for billions and billions of data sets on a street image, all these things. So during their controlled environment, the performance is best. But when they drive the vehicle in the real road, on road, it makes mistakes. It hits someone, but they don't have any idea why it made a decision like this. Even though it knows it is an other car, it still hits the vehicle. But if they try to debug why that particular algorithm, even though it is a deep learning algorithm, if they try to debug why it made such a decision, it is going to be very difficult, because features are extracted on its own by the deep learning algorithm, and we have no idea how these features are extracted. So that is the problem. So when we deploy these kind of deep learning algorithms for such applications where a failure is, you can say it is a fatal. If a deep learning algorithms makes a wrong decision, it turns out to be fatal. So in such a case, we cannot use deep learning algorithm to do this feature extraction. So they will go for traditional handcrafting feature extractions, because they can explain. If it makes some bad decision, they can explain why it goes wrong, all these things. So there is a different field now in deep learning that is called as explainable AI. Where people are able to learn why the deep learning algorithm is making this particular decision, on what basis, all these things.
Okay, sir. Thank you. Can we go for feature concatenation using these conventional algorithms?
Sir, actually, I am putting this. I am just talking about this conventional algorithm and its drawback. Okay. And then I will talk about deep learning algorithm. So I have prepared this slide for that only.
Okay, sir. Okay, you carry on, sir, please. Thank you.
Okay, sir. Thank you so much.
Thank you.
Okay. So this feature extraction requires a specialization, and then whatever the feature we extract, generally it should be robust to many things. So say for example, here is an image which is same image taken with different perspective. Okay, so if you ask this question whether all images are same or different, it looks like different, but they are all same. Okay, so feature extractor should be robust to this viewpoint variation, and it should be scale invariant. Whether it is small image or big image, the feature extraction, I mean the feature that we are using, should be robust to all these variations. And the second most important thing about this feature extraction is that it should be robust to illumination. Okay, say for example, again, if you consider autonomous driving vehicle, okay, so I should not just, where the illumination in the real world is very challenging, right? Because even human beings struggle a lot to drive during the night. So we see the same streak during the day as well as during the night. So the illumination plays a key role in recognizing all those objects. So it is extremely difficult to deal with the illumination variation. Okay, so again, feature extractor should be invariant to the illumination. That is what we expect. Then the third, like this, we have some sort of challenges like occlusion, all these things. So what really happened in the previous case is that even for simple applications, even if you choose a particular feature, it will not be robust to all these variations. Okay, they may be robust to some variations, say for example scale invariant or shift invariant, all these things, but it is not robust to illumination invariant. So we have to pay attention on deciding the particular feature. Okay, so you can just search through Wikipedia to see how many features are there in computer vision domain. Okay, it will list out some n number of features which are tailored to a particular application. Which means if I use if some people have used the shift feature for some application, you cannot use the same shift feature for some other application. So you must have to make a decision based on whether it is suitable to this particular application or not. So it requires some sort of specialization in feature engineering. So one of the major limitation of conventional ML, and there are many, but if I want me to point out one more, you can see the one more important is it is not scalable. So what do I mean by that? Suppose, let us again take a specific example. If I want to use image classification, if it is a binary image classification, I need not to go for deep learning algorithm. I can simply do feature engineering and use some support vector machine to do that. Suppose if number of classes in my task goes beyond 10 or 100, okay, so which means okay, let me take again a specific concrete example to illustrate this. As I told you already, there are 10,000 real world objects are there. Okay, so when I say objects, it is a physical, it is made, it is some kind of physical object, right? Like chair, even what is bus, car, cat, dog, all animals. Okay, so if you keep on counting, it will go beyond 10,000. Okay, suppose if I wish to develop some classification algorithm, if I decided to use only 2 classes, okay, so which means I pass an input image to this classification algorithm. My objective is that I have to recognize the class or the objects inside this image belongs to which class out of these 2. Again, if you consider dog versus cat, okay, if my input image contains dog, it has to say it is dog. If it is cat, it has to say it is cat. If it is neither dog nor cat, it has to say other, something like this. So totally what I have 3 classes here. Okay, so you can either post this as 3 class problem or 2 class problem. So this is okay if this is my problem, then I can stick with conventional ML. Okay, but now let us assume I'm going for 100 classes. Okay, which means the setup remains same. Again, I have a classification algorithm. Again, I'm going to pass an image, but now this image may contain any object from this 100 classes. Okay, then the task of this classification algorithm is to categorize or identify which class this image actually belongs to. Okay, now it may belongs to any class from 0 to 99. Say for example, if I number the classes from 0, then it should be up to 99. Okay, so can I use SVM classifier now? So the question is, it depends, but in general, usually we cannot use SVM classifier. Okay, because of there is something called as curse of dimensionality. All these things are there. So when you scale these SVM classifiers for this sort of large class classification, okay, they often fails. Okay, it is reported they often fails, which means if you move for 1,000 classes, okay, so from 100 to 1,000, okay, so now my image may belongs to any class out of these 1,000 classes. Okay, we cannot deal these sort of problems with conventional machine learning algorithms. Okay, again, we cannot do future engineering, which means we need to identify a future that distinguishes all these 1,000 classes. Okay, which is quite impossible. Handcrafting all these features manually to distinguish all these sort of objects is quite impossible. Okay, so in such a case, we go for deep learning algorithms. So that is what we mean by scalable. Okay, so even can you scale it to 10,000 objects? It is quite difficult. Even with the today's deep learning algorithm, when you go for 10,000 classes, okay, they abruptly fails. Okay, so it is extremely difficult. Okay, so because of this scalability, people like tech giants, Google and Facebook and IBM, no matter which tech giant you pick up, they at the back end they will use some sort of deep learning algorithm for their application. Okay, so it is not only for computer vision, even for speech recognition. Okay, they totally rely on these deep learning architectures. Okay, so probably you might have heard something called as DeepMind. Okay, they are doing a phenomenal task in applying these deep learning architectures to solve many problems like game. Okay, playing, like probably you might have your Go game. And then recently they have made a breakthrough in biology by constructing a protein structure. Okay, which is quite impossible with the traditional algorithms. Okay, so they are making a breakthroughs. Fortunately, all those breakthroughs are happening. Many of their architectures are actually have one core operation, that is convolution operation. Okay, which means if you know what is convolutional neural network and how it operates and how to construct one convolutional neural network architecture, then you can solve many sort of problems. Okay, so that is why CNN plays a major role in deep learning because you can convert any data into an image, whether it is a speech. Say for example, even in speech recognition, you can take a speech signal and then you just convert that into a frequency and time domain image, and then you can make use of this image to pass as an input to CNN. Okay, fundamentally CNN takes an image as an input. So once if you are able to represent any sort of input data as an image, you can deploy CNN to carry out the rest of the task. Okay, so as a quick summary, so I have been discussing a lot. As a quick summary, this is what that all things else about in the past as well as in the present. Okay, so in the present we have a classification algorithm, we have deep learning algorithm. So but if I want to give you the summary of classification algorithm, there are a lot. Okay, so MLP, which is a very old classifier, okay, multi-layer perceptron, and then you can even use decision tree for a simple problems, especially if your data set is containing categorical data. But trying to applying decision tree for image is fatal, so don't do that. And then HMM, CNN, RNN, all these are very recent. Okay, so we have plenty of classification algorithm. So by default, today, if you go for image classification, this must be your choice. Okay, so first you have to build or you have to make use of the existing CNN, or you can build your own CNN. You can test with it. You need not to bother about the rest. Okay, because of their superiority in outperforming every other task, you can try with CNN. In the past, this is the present scenario. In the past, we had only one more stage. Before classification, we will have something called as feature extraction. Okay, and again, please take a note of it. I didn't mean feature extraction is absolute. Okay, they are not no longer used in today's industry. They are still there where a reliable output is required. Okay, so you can apply this deep learning CNN architecture for some where the error is tolerable, even if the CNN architecture makes a wrong decision. Okay, and it is not fatal. It is, if it is tolerable, you can deploy it. But if you think of an application in medical side, all these things, especially again in autonomous driving vehicle, so we cannot simply rely on deep learning architecture. Where the feature extraction, handcrafted feature extraction might be helpful. Okay. So of course, in 2012 or in 2011, if I remember correctly, one student, you know, Alex Krzyzewski actually came up with a scaled CNN architecture. So today, if you go for object classification, okay, if your image contains a single object, okay, and again you recall where you can apply all these things, the condition is that your image must contain only single object. Okay, but in natural images, the image may composed of multiple objects. That is a different scenario, but here we assume that the image contains a single object. In this case, if I want to classify what is an object in that image, you can use any of these nets. By the way, LeNet is the first convolutional neural network architecture proposed by Jan LeCun. Okay, I think in around 1990s. Okay, since then people didn't care much about this CNN architecture. Even all the CNN, RNN were proposed in 1990. That was an era where these architectures were developed quite rapidly. Sooner they were dropped because of SVM. Okay, so SVM took into the domain and it remained there till 2010. Now these architectures are coming back. Okay, because of now computational resource is not that quite difficult. Everyone have some sort of computational resource. So now people have modified these architectures. Okay, so AlexNet is, you can think of it is simply scaled version of LeNet. Okay, by introducing different activation function, all these things. So these are all the most commonly used CNN architecture for single object classification. Okay, so VGG is actually used for face recognition, and then ResNet is a kind of now it is a standard architecture. Okay, ResNet 50, ResNet 101, all these things are there. Okay, So what is the, okay, so I don't want to dwell a lot in the history. So let me skip few slides ahead. So as I told you already, this is the scenario today. Okay. And this is a really a big bottleneck for industry. Okay. So if your deep learning algorithm doesn't work, if you ask this question why, you cannot answer. Again, if it works and if you ask this question why, again it is not possible to answer. Okay, so it is extremely difficult. So that is where people are now moving to focusing their attention on explainable AI. Okay, they want to explain why this particular architecture took this particular decision. Okay, so what made it to take this took this particular decision. Okay, so they want to reason it, and it is now getting popular. Okay, so your next, again the scenario remains same. I pass an input image. Again, the classifier gives the class, not only class, it also gives the reason. Okay, it also justify why it thinks this particular image belongs to this class. Okay, so it is not a kind of human thinking, it is a computer thinking. Okay, so it is not exactly like human thinking. So this is trending now. Okay, so suppose if you are a research scholar or anyone who want to expand your horizon, okay, from just classification, you can go for this reasoning thing as well, or you can look into this explainable AI. So you maybe already know all these eye-catching applications of deep learning algorithms. And one more thing often people don't pay attention to is this one. Okay, so you can see, you might have a sketchy gone where the input is just a cartoon or a sketch. So it will retrieve all the images that resembles this particular sketch. Okay, so you draw this sketch on a notepad or something and you pass this as an input image to your deep learning architecture, then it will return an image that resembles this sketch. Okay, so you can think of many applications where it can be used, like in Forsenic, where people will draw some sort of an image of an culprit. Probably it will generate real facial resemblance from this cartoon image. Okay, so if you list out all these things, applications of deep learning, it simply goes on. It's infinite. So other than this CNN architecture, CNN plays a major role. Even inside this GAN architecture, there is a part of CNN. Okay, so it is a generator and adversarial networks where it is composed of CNN as well. Okay, so there are applications today which were considered impossible in the past. Okay, these, you might know all these applications, right? Probably you might have used this in your mobile app. Okay, so face app applications. So you cannot imagine these kind of application with conventional machine learning algorithms like neural style transfer and this kind of manipulation. Okay, so this also brings this challenge. So why am I posting this here is, this is a challenge, right? Anybody can take any image in the internet, they can manipulate it in such a way that we cannot distinguish whether that image is real or not. So it is really a biggest threat to the entire community, especially Indian community, where people can take an image and then manipulate and then they can circulate it in the social media. Okay, so where the common man cannot distinguish whether it is in real or fake. Okay, so this is again a great challenge, and people are like Adobe are working on an algorithm trying to distinguish whether the given image is a fake image or a real image. So this image is actually fake image. Okay, we have no way to judge whether this is a fake image or real image, but this is a manipulated image. Okay, so it is now you can think of this era 2020 as a war between AI and AI. Okay, so one AI algorithm, so when we cannot say AI, probably DL algorithm, trying to generate a real image, another AI algorithm is trying to detect whether the image is real or not. Okay, it is really a big war. So you can focus on these areas as well. You can do some sort of projects in these areas as well. Okay, so probably you might have been introduced. So father of, you can call these people Geoffrey Hinton, Then this is Alex Krzyzewski, a PhD scholar. Okay, worked. The supervisor is Geoffrey Hinton, and then they proposed this AlexNet. One thing is that these people, Jan LeCun and then Geoffrey Hinton, and then there are many, they have been working on this deep learning for the past 15 years consistently, okay, or even since their PhD. But the result comes, they obtain the fruitful result only after 20 years of hard working. So okay, you can see that only in the year 2017 they got the citations. Probably it is very much important for people, faculties, right? Faculty members. His paper has been cited 74,000 times in 7 years. Okay, but this work is actually, they have these ideas and they keep on consistently working towards these ideas for the past 15 years. Okay, so if you have a convincing idea, so that is what Jan LeCun always says, if you have a convincing idea, don't give up on it. You keep on working it, one day you will achieve something like this. Okay, you know all these operations. Again, as a quick recap, since it is an ConvNet applications, AlexNet, VGG, GoogleNet, as I just listed out earlier. So these are all the most commonly used ConvNet architecture for single image object classification. Okay, and one important core operation. So it is very important, whether you are coming from an image processing background or a computer science background, or if you have no idea about this convolution operation, please try to pay a lot of attention on learning what this convolution operation is actually does. Okay, so again, I would like to take a simple example. You can call this as kernel, okay, or filter. Okay, so this filter size is 3 cross 3. Okay, so every convolution operation requires kernel of any size, 3 cross 3, 5 cross 5, 1 cross 1, and an input image. Okay, you will carry out convolution operation between two modalities, okay, two functions. So one is a kernel and another one is an input image. So if it is an input layer, we call this as an image. If it is an intermediate layer, we may call this as blob or something like a different name. Okay, so in this case, the size is 3 cross 3, right? Which means there are 9 elements. But for this case, we have set all these values to 1. We don't bother about this. So I can say there are 9 parameters. Okay, so this particular kernel is having 9 parameters. So convolution operation, what it does is, we will simply move this kernel on an input image, right? So here an image is padded with zeros. Then we simply move this kernel over this image, and then we simply do a dot product operation. Okay, so I just multiply 1 with 0, all these things. Then let us say I have an image of size 1, 2, 3, 4, 5, 6, 7, 8, 9. In this, suppose if this is an image value at this particular region, I simply multiply these 3 cross 3, a small portion or a local area in an image, with a 3 cross 3 kernel, right? So it is a dot product. So it is 1 into 1 plus 2 into 1 plus 3 into 1 plus 4 into 1 all the way up to 9 into 1. So you have to simply sum it up. It is simply summation, right? You sum this, you will get some number. Okay, so you will get some number, you just divide that number by 9. So the key takeaway is, my 3 cross 3 filter multiplies with a 3 cross 3 region in an input image, and then it produces one number. That number goes here. So we call the output as activation map, okay, or feature map, whatever you wish to call. So again, now we move this filter by 1 unit, 1 pixel unit. So this moving operation is called as stride. Okay, so now if I set strides equal to 1, what happens is that I will move this kernel 1 pixel along the horizontal axis. Okay, then again I will repeat the same operation. Now you know it is 90 into 1 divided by 9, so it will return one number as an output, and then I will store it here. So we will repeat this operation. Again, I will next move this kernel 1 unit horizontally, and then once it reaches the end, then we will move this kernel down 1 unit vertically. Okay, so this is convolution operation. So we repeat this, keep on filling this entire matrix, output matrix or activation map. Okay, so this is convolution operation. It's a traditional convolution operation. Even if you, this is a fancy word, right? So it is called as convolution. So if you don't like, you can even say it is simply dot product. With consistent with the mathematics, it is simply a dot product in mathematics. Okay. So the question is, what is being learned? Before answering that question, again I wish you to remember this. So I have a kernel of size 3 cross 3. Then I have this 9 parameters in a kernel. Okay, I don't know what is the value of these parameters. They are randomly initialized in deep learning. Let us say I have 9 elements in a kernel. All these 9 elements are called as 9 parameters. Okay, so the question is, what is being learned? Okay, so this actually distinguishes deep learning from the conventional machine learning. So if I have an input image and if I apply a kernel of size 3 cross 3 with all elements set to 1, 1, 1. Okay, so it actually blurs an image. So if you increase the kernel, the blurring is more. Okay, so you can go for 11 cross 11 or 21 cross 21. You can see the blurring is more. Similarly, I can put some other values. Why should I stick with 1, 1, 1? Okay, I can try out with some other value, 1, 1, minus 1, all these things. So how do we decide these numbers? So it is actually from image processing. So you don't need to bother about these numbers. Suppose you just take it for granted. If I put all these numbers into this kernel, and if I apply this kernel, if I carry out the convolution operation for this image, what do you get? You will get an image. Okay, so again, this particular kernel acts as an edge detector. Okay, so these are all traditional kernels used in image processing for simple applications. Okay, so the question is, how do we decide these values? I'm putting all these values. I'm putting 0 here, here I'm putting 1 by 9. So there is a strong mathematical knowledge, mathematical concept is behind these numbers. But in deep learning, what we do is we simply create a filter without putting these numbers, and we randomly initialize this filter. Okay, I am putting numbers randomly. I don't care what numbers goes here, even 0, 0, but not all zeros. Probably 0.1, 0.2, 0.3, again 0.01. Okay, so before training, I'm just initialize all these filter. Okay, randomly. So when we talk about randomly, this may come from any distribution. Oftentimes it is normal distribution. Okay, so suppose, let us assume that, suppose if I build a deep learning algorithm where I pass an input image and then I expect the output image as a blurred version of the input image. Okay, so input is an image, output is also an image. Now the task given to the deep learning algorithm is to blur this image. Okay, suppose if I initially I just create this kernel and initialize with all these values. Okay, so after training this algorithm with n number of images, okay, where now after, say for example, 1000 epochs, my deep learning algorithm learned to blur and give an input image. Okay, so after 1000 epochs, if you look into the kernel values 3 cross 3, amazingly, it had now this kernel value will have a high resemblance with this kernel values. Okay, either it may converge to 1 by 9, or it may converge to some other Gaussian distribution values. Okay, so now we are asking this deep learning algorithm to learn these values. Okay, so in traditional or in conventional ML or image processing, we set these values, okay, based on our mathematical knowledge, based on our derivations, pages and pages of derivation, we set all these values, okay. But now the scenario is entirely different. Now we are asking the deep learning algorithm to learn these values, okay, what values should goes here and goes here, each element values. So in this case, we have only 9 learnable parameters. Okay, so this is the core idea. So now we are carrying out one convolution operation with one kernel. If you understand what this convolution is and what is being learned and how this is how everything works, then we can simply extend this idea. Okay, so the convolutional neural architecture is simply the extension of this idea. Okay, and again I need to pause. Okay, we may take a 5 minutes interval. So you take 5 minutes interval, a 5 minutes break. And if you have any questions, you can ask during this 5 minutes break. Okay, so if you have any questions, you can ask now, or I may move on to the next topic. Okay, so I think now we move on to the topic, and before that, I would like to emphasize how to build a convolutional neural network. So, as I as I just mentioned in the previous slide, that each convolution layer is comprised of many convolution kernels. Okay, say it may 3 cross 3. Okay, let us say I have only one kernel. Okay, then and also let us say I have an image, and again for the sake of simplicity I am taking 10 cross 10 gray image, and now probably 32 cross 32. This will be much better. And we know that these images are composed of 3 channels, right? Red, green, and blue. So the first one is red and green and blue. So we can think of this image as a blob, okay, which has the depth. So every input image may or may not have a depth based on the type of the image. So it is 32 cross 32, and since it has 3 channels, we say the depth is 3. Okay, and to carry out this convolution operation, okay, so the convolution has to happen along the depth, okay, not only along the spatial dimension, it has to happen along the depth as well. So if I use one kernel 3 cross 3, okay, 3 cross 3, and since it contains, my input contains 3 channels, or the depth is 3, then the kernel should also, the depth of the kernel should also be 3. Okay, so this kernel will act on this input image and produce one activation map. Okay, so even though my input image is 32 cross 32 cross 3, each kernel in the convolution layer will act on an image and produces only the spatial output. Okay, so probably size lesser than that, but by appropriately padding with zeros, you can keep the spatial dimension as it is. Like this, I can define n number of kernels. Okay, it is kernel 1, and then I can use one more kernel, kernel 2. Like this, I can keep on adding as many kernels as I want. Okay, and there is no strict rule on how many kernels should be there in a convolution layer. Okay, so you might ask, if I build the first convolution layer, so now we will just give the oral description without all these things. We say kernel size, let us say 3 cross 3, number of kernels, okay, let us say 6, okay, and then possibly what sort of activation function you are going to use, probably ReLU, all these things, right? These are all the parameters that we have to pass in order to build the convolution layer. But the question is, why you are going for 3 cross 3? Why not 5 cross 5? You might ask this question. Or why you are going for only 6 kernels in the first convolution layer? Why not 60? Okay. Then why you are using this ReLU activation function? Why not tanh activation or sigmoid or some other leaky ReLU, or even the most recent one. Okay, it's a very controlled leaky relay activation functions. So for every field, kernel size, number of parameters, activation, we have plenty of choices. Okay, you can pick any one from out of many choices. Then we call this as hyperparameters. Okay, and all of the choices makes the decides the performance of the CNN. Okay, so we have to make some sort of educated choices in order to expect good performance. Okay, so we have to make a convolutional neural network architecture and even number of convolution layer. You might ask the next question: if this is a convolution layer 1, how many convolution layer we need to create? Okay, whether 2, 3, or 10, or 100, or 1000. Okay, so again, this is our choice. Again, this falls into the category of hyperparameter. Okay, so we have to, okay, because by properly padding, you won't run out of the dimension, so you can add as many convolution layer as possible. But always the better thing is you build, suppose if you wish to build a convolution neural network on your own instead of using the existing CNN, you start with some 2 to 3 convolution layer. You start with very small region 3 cross 3 and use incrementally increased kernels. Say for example, if I use 12 kernels in the first convolution layer 1, so in the second convolution layer I can use 24. There is no reason why I picked up exactly 24, so we are just going in multiples of 2, so maybe 48. Okay, so you build a small convolution layer, small number of convolution layer, and then you pass this input to the fully connected layer, and then you just run this for few epochs. Okay, say for example, you run this for some 10 epochs and you note down the performance. Okay, so we will note down the performance of the architecture either using accuracy or loss. Suppose if I pick up loss over 10, and then if I note down how the loss decreases over each epoch, and you might probably see some kind of curve like this. Okay, this is very ideal curve. We may not get these kind of curves. Okay, probably after some epochs the loss remains constant, or probably it may increase. Okay, so in such a case we may stop here, so we call this as early stopping. Okay, so these are all some sort of mechanism to build to decide which convolution layer is or to decide which CNN is better. Okay, so like this you build a simple connet and then see how the performance of the CNN in terms of loss and accuracy, and then you have to decide whether adding additional layer will be helpful or not. Okay, so all these things again based on the conceptual understanding of each component of the entire CNN. Okay, so oftentimes what I observe is that many of us tend to simply build the con layer because we have the framework, right? So either you can use Torch framework or Keras. So you build a convolution layer randomly, then you simply train it and it works or doesn't work. Okay, but this is not a good approach, especially when you create your own convolution layer. Okay, so if you are using the existing architectures like ResNet or GoogleNet, it's all right. But if you are about to solve a new problem where nobody have built any CNN for that problem, so in such a case you cannot do all these things randomly. So for there you have to make an educated guess or educated decision there. So you can make such a decisions only if you have solid knowledge on the functionality of each components or each parameters in the convolutional neural network. Okay, so and also you have to keep track of the performance and as well as the computational requirement. Okay, so you will say one one CNN architecture is better than other CNN architecture only either you have to show the improved performance, even if the least performance you say it's a computationally it is efficient, or you say the number of parameters are less compared to the other CNN architecture. So these are all the things that distinguishes that showcase our convolutional neural network architecture is better than the existing one. Okay, so No matter what sort of application you are going to work on, whether classification or object detection or image segmentation, the paramount importance must be given to understanding this data. Okay, so usually we know what image is. So for classification problem, it is not that much difficult to understand or how to um, build a data set on our own. Okay, even though we can use the existing data set if it is readily available. If it is not available, then we have to create our own data set, right? So creating own data set requires some sort of skill. So you will decide on all these things. Understanding data and organizing the data in a proper way is much important. So you create, suppose if my problem is classification and I have only 2 classes, so I have to keep 2 folders like this. Okay, so this is true whether you are using a TensorFlow framework or Keras framework or PyTorch framework or even MATLAB. Okay, so organizing your samples or images in a proper folder is mandatory requirement before using any framework. Okay, and then you also recall that every image, say for example, here I have put all these images in a training folder or as well as in a testing folder. Okay, and also I have to label these images. Suppose if it is 2 class, we will label this as 0 or 1. Okay, or if we use one hot encoding, we will label this as 0 0 or 0 1. Okay, so I hope, suppose if you don't know what this means, you just note down all these words. So if it is a classification problem, you can use one hot encoding, which is quite straightforward. You can use an inbuilt functionality. What it does is it will simply stretches this categorical number 1 2 3 4 into sort of binary representation. Okay, so suppose if I have 2 there, then I will use 3 bits, 3 zeros. Okay, I will use probably like this 1 0 0, something like this. Okay, so sorry, 0 0 1. Okay, so this is what we call it as one hot encoding, and there is a reason why we go for one hot encoding. Why don't we stick with these numbers? Okay, so I will talk about this if we have a time. Okay, so oftentimes this labeling process consumes a lot of time. Especially this labeling is easier if number of classes are very limited, especially 2 3 or even 10. But this labeling procedure, manually labeling everything, will take a lot of time if you have 100 classes or 158 classes. Okay, in such a case, you cannot ask someone, even your students, to sit and label every images. Okay, so again, if you should organize your image into another folder. Here I have a cat and then dog, right? So if I have 100 classes, I can create 100 folders. So inside these folders, remember these are all folder names. So inside this folder name, inside these folders, I will put all the cat images. I don't care about what is the name of those images. If I have a cat image, I will keep inside this folder. If I have a dog image, I will keep inside this folder. Even you can automate this process. Okay, so you need not to go and download everything from Google one by one. So if you are good at Python have a supporting package where you can retrieve all those images, that we call it as web scraping. Okay, so if you are about to deal with thousands and thousands of images, okay, so you need not to download each image individually by right clicking and save image. So again, you can make use of Python, and Python will take care of it. Okay, but this is the folder structure you have to follow for classification. We will have a different structure for object detection. We will have a different structure, or sorry, different labeling procedure for object detection, and then different labeling procedure for object segmentation. Okay, so again, I would like to highlight how it look like for object detection. So in object detection, my input image may be comprised of many objects. Okay, so in object classification, my input image contains only single object, right? Single object. But in object detection, my image may contain single object or multiple objects. Okay, so in such a case, I have to localize the object. Say for example, my image contains cat as well as dog. Okay, if this is my input image, in object detection, first I have to recognize where the object is. Okay, I don't care what the object is. I will say where the object is, and I have to mark with a bounding box. Okay, so if they are different objects, then I have to mark the bounding box. So I will take these coordinates, the diagonal coordinates. Okay, say for example, if this is x0 and y0, if this is x1, y1. Okay, similarly, I will take the coordinate of these two. Okay, so like this, for every object, we will create a bounding box around that object, and then we will take this diagonal xy coordinate. Okay, and this xy coordinate will be stored in a field called as annotations. Okay, which contains xy coordinate for each object inside an image. If my image contains 10 objects, so for each object the xy coordinate will be stored in something called as annotation. Okay, so this this is to deduct the object with a boundary, and then I will use the classifier for that. Okay, so this labeling procedure is entirely different. So if it is a segmentation problem, then I will draw a map around it. Okay, say for example, if it is cat, then I will fill it up. Okay, I draw the boundary and fill it up. Then we call this as mask. Okay, so for each object in an image, I will create a mask. Then I will store that mask as a label. Okay, so understanding the data and its label is quite involved. So before working on your application, you must pay attention on understanding the data and creating all these masks or annotation. So if they have already created all these things, that is quite better. Otherwise, we have to create all these masks and annotations on our own. Okay, there are many tools where you can use all those things in order to create all this labeling. Okay, so having said that, now let us illustrate this convolution layer, all these things with an example. So here, yeah, they call this as a filter, but here the file size is 5 × 5. Then this 3 actually represents this particular filter is going to act, and I am not saying this is an input. Okay, sorry, this is an image. Do not call this as an image. Let us just call this as an input. Okay, it may be an input from the previous layer, or it may be an input itself to the first convolution layer. So what we need to focus is that my input contains the spatial dimension of the input is 32 × 32. The depth is 3. Okay, so here I am deciding what is the size of the kernel. Spatial size is I am setting this as 5 × 5, but it could be 3 × 3 or 7 × 7, whatever. But the depth must be equal to the input depth. Okay, so oftentimes you need not to pass this depth argument because it will be inferred automatically by the framework. But again, if you are constructing the coordinate from the scratch, you need to decide all these things. Okay, but I will encourage always to construct the coordinate from the scratch instead of using the framework's functionalities. Okay, so now it will act on this input, and then it will produce one activation map, right? So what it does is it will produce one activation map, that is 28 × 28 × 1. Okay, so what this circle actually represents is that after this convolution operation, it will return only one number, right? So previously we just looked into that. I have an input local area. So in this local area, I am using a kernel. I am carrying out a dot product. After dot product, it will return one number. That one number is going to this node, and this node is actually an activation node. Okay, so you can use any sort of activation here, sigmoid or relu, and then it will output some number, either 1 or 0. Okay, so based on the activation value. So that will be stored in an activation map. So this is what happens if I use one kernel. So like this, if I use 6 kernels, all of size 5 × 5, then it will, the output from the convolution layer. Okay, so let us say this is a convolution layer 1, and if I have used 6 kernels in the convolution layer 1, if this is an input to convolution layer 1, my input is now transformed into a 28 cross 28 cross 6 blob. Okay, this is an output from convolution layer 1. So optionally you can add max pooling layer. This is just an optional. Otherwise you can go to the convolution layer 2. Okay, so in this case 10 refers to there are 10 kernels used in convolution layer 2. Okay, so the spatial dimension probably 5 cross 5, and then stride probably 2, not 2, so probably 1. Okay, so there is a reduction in spatial dimension. See, the spatial dimension is 32 cross 32 in the input side. After first convolution, we have some optional parameters. I hope you might already know all these formulas. So it is an input width minus the filter or the kernel size. So if I have added padding, you will add padding, and then you divide this by stride, then plus 1. Okay, so this is an output dimension given the input dimension. So if it is a square image, H and W are going to be the same. Okay, so you can see if I don't use any padding, if I set padding is equal to 0, what is the consequence of setting padding is equal to 0? So what really happens is that as this input moves into the convolution layer, the spatial dimension is keep on decreasing. Okay, at one instant the spatial dimension will be extremely low, but the depth will the depth of that output may be very higher. So here the depth is, you can see it is a depth is 3. After first convolution layer, the depth is 6. After the second convolution layer, the depth is 10. Okay, so I would like to ask only one question here. So can you tell me how many parameters are there in the first convolution layer? Learnable parameters. Okay, my first convolution layer contains 6 kernels. Each kernel is of size 5 cross 5 cross 3. Then how many parameters are there? So if you have understood that, that would be great, because keeping track of number of parameters introduced by each convolution layer or fully connected layer is important. Because if you add more and more layers, then you are adding more and more learnable parameters. Probably you will render your network into an overfitting problem. Okay, shall I show you one example and then ask the question again? Or you already know how to compute how many parameters are there in the CNN? Okay, so again, let me show you how to compute that. So so how do you calculate number of parameters? Okay, so my kernel size is 5 cross 3, which means how many elements will be there? There will be 25 elements in one kernel, then one bias. Okay, or you can ignore this bias. So I will have this 25 elements in one kernel. Then I am using 6 kernels, right? So each kernels we have 25 learnable parameters. So it is 6 into 25. So for each layer we will have one bias unit. Okay, so it is therefore there are 6 kernels, there are 6 bias unit. Okay, so this is how you have to calculate number of parameters. Similarly, so if you come here, each kernel is now 5 cross 5 cross 6, which means 25 into 6. 25 into 6 parameters in a single kernel, and then there are 10 such kernels, so into 10, and then there are, for each kernel I add one bias, so plus 10. Okay, so like this you should keep track of the learnable parameters in your entire network. Okay, so that's what I'm here. Okay, so optionally you can add pooling layer. So there are many types of pooling: max pooling, average pooling, even you can build the pooling based on the entropy, but that is quite involved. So let us focus on this max pooling. So it's very simple. It reduces the dimension. So you take the filter size as 2 cross 2, and whatever the maximum from these 4 elements, okay, then you take that as an output. Okay, again you repeat the same. It is a crazy idea. Why should I take only the maximum element? Doesn't mean that I'm ignoring all these values. So if I ignore all these values, I'm losing information, right? So max pooling is okay if your convolution layer have a lot of redundant information. Okay, there using max pooling doesn't do much harm to your network. But if you look into the con layer, and if you see there is a not much redundantation and all these values have high correlation, then applying max pooling layer to this output of a convolution layer will be a fatal decision. Okay, so for that you have to look for some other pooling methods. Okay, so now the purpose of max pooling layer is to reduce the spatial dimension. Okay, it will not disturb the depth of the convolution layer. Say for example, in the previous case, I have an output from the first convolution layer, which is 28 cross 28 cross 6, right? The depth is 6. Now if I apply a max pooling to this convolution layer, it will only reduce the spatial dimension. So now it will reduce it to half, 14 cross 14, but the depth remains same. Okay, it will not disturb the depth. Okay, so it only reduces the spatial dimension of all the activation marks, not the depth. Okay, so this is very important. So like this pooling layer is purely optional. It is not mandatory. So first, if you say convolution layer, it is just a convolution operation. Oftentimes this pooling layer is also associated with the convolution layer, but it is purely optional. Okay, so following that, you can apply all these regularization techniques to avoid this underfitting and overfitting to data, input training data. I hope you know all these things. Maybe you might already have been exposed to this concept, regularization technique, all these things. So again, let me try to give you a simple intuitive explanation for why regularization technique is good. Let us assume I have a trained model, or sorry, I'm building a CNN model. So I am using training data to train my CNN model. Then I'm looking at the accuracy of the training on the training data set. So it says the accuracy is 99.99. Okay, so I am thinking, okay, my model is performing well. So what I'm doing is I'm taking this CNN, the trained model, CNN trained model with the trained weights. Now I am passing this testing data, okay, which are not used during the training process. Okay, so therefore we can say this testing data is unseen by the CNN model. It is new to CNN model. Now I am measuring the performance on this testing data. So if it is, say for example 90, that is all right. But if it is 50, okay, so then there is a huge drawback. Okay, so my model performs well on the training data. Okay, then I assume that it performs well in the real world. But before that, I am testing on the testing data. The performance is decreased drastically. Okay, so we call this as overfitting. Okay, so you can use the word bias and variance, technically speaking, but we don't need to use those words. Let us say my model is overfitting on the training data. Okay, so it learns well the training data, but it is unable to generalize it to the testing data. Okay, if my training accuracy is low, okay, my testing accuracy is also low, then we say it is underfitting. Okay, so probably you may learn this as bias and variance. Okay, so this is the right word to talk about it, but intuitively we can say like this. Okay, so only if my accuracy for both the training as well as testing is acceptable. Say if my training is 99, my testing at least 90 or 89, that is acceptable. Okay, then we can say it is neither underfit, it is not overfit, it is properly fitted. Okay, so what is the way to improve this overfitting or underfitting, or eliminate this overfitting or underfitting? So if you want to eliminate underfitting, you have to go for a new model. Okay, but if you want to eliminate overfitting with the same model, so then you can try out with some regularization techniques. Okay, and there are plenty of regularization techniques, but the most commonly used one in terms of the performance is dropout. Okay, so again, the idea behind the dropout is very nice. So you can just take the paper and then just go through it, how it works. Okay, and then you can use batch normalization. So otherwise you can use this L2 regularization techniques. Okay, then once if you apply dropout, batch normalization and L2, or once if you incorporate all these into your CNN model and then you retrain your CNN model. Okay, now you can see probably training accuracy is 97. So during testing, you won't use these layers, dropout layer or L2 regularization or batch normalization layer. Okay, probably you can use batch normalization. So during testing also you will get some around say 88. Okay, so the same model, there is no change in the model architecture. Only thing is we have added a regularization technique into that architecture. Okay, now it performs well. Okay, so these components are also used while you build CNN architecture. Okay, you can use k-fold cross validation, all these things. Okay, so finally, I would like to talk about this performance comparison. So you can use either top 1 error or top 5 error. Okay, so top 5 error means, say for example, I have a CNN model. Let us say I have 10 classes. Okay, then I am passing an input image to this CNN model, and the CNN model will give me 10 numbers as an output. Okay, so this is a probability distribution. So this is for the first class and this number is for 10th class. Okay, so whichever have the higher probability will be considered as the correct prediction. Okay, so let us say my image belongs to, my input image belongs to class number 3. Okay, but the CNN predicts the image belongs to class number 2. Then I say it is an error. Okay, so we call this as top 1 error. Okay, so whatever have the highest probability, I am considering this. But top 5 error means, what do I do is, I have this prediction by CNN, I have all these numbers, so this is the highest probability, a class having highest probability, and I also consider the next highest probability. Okay, so probably it is class number 8, the second higher number in the higher probability, and then class 3 is at third higher number. Okay, so like this I am picking up top 5 higher probabilities. Okay, so if my input image belongs in any of these top 5 probability prediction, then I will say this is a top 5 error. Okay, so even though it is not giving highest probability to the correct class, it still predicts it belongs to the prediction belongs in top 5 classes. So when should I use this top 5 error? Not for 10 classes. So if I have 1000 classes or 100 classes, then using this top 5 error makes sense. Okay, it is alright. People in general accept this top 5 error as the performance criteria. So this is one performance. Looking into the error is one performance criteria. The other performance is how long it takes for inference time. Okay, so you can see, even though the performance of the ResNet is better, but the inference time by the ResNet is extremely poor. Okay, it takes around some 900 milliseconds to make a decision. Okay, so in like that you can compare this with model size. So here model size actually the number of parameters in the model. Okay, so if you calculate the number of parameters, here you can see VGG19 have some 550 million parameters, right? So the unit is now in millions. 1 million means there are 10 lakh parameters. 10 million means there are 1 crore parameters. So if the number of learnable parameters are high, then it takes a longer time to train the model. Okay, you need a lot of computational resources to train your model. Okay, so well, compared to this VGG19, AlexNet is relatively small. Okay, so which is 200 million parameters. Okay, so you can put together all these parameters into a single graph. Okay, so the x-axis is top error, top one error, the y-axis is inference time, and the size of the circle denotes the model size. Okay, so if you organize everything into a single graph, then you can pick up, you can make a right choice of the model for your application. So if that is the case, probably ResNet 50 is better in terms of top one error, in terms of inference time, in terms of model size. Okay, so which means it will give you quick inference during the testing, and also it will run on a simple, not simple processor. So it might run on a simple computers, okay, which doesn't demand much memory resources, okay, because the model size is quite relatively small. So having said all these things, I think it would be better if you take a quick hands-on. It is now 12 o'clock. So let me finish the concept, and during the afternoon session we take it hands-on. Okay. So, let me skip ahead all these things. This is for object classification. So for object detection, again, this is another research field. Okay, so you can work on classification or detection, but it is not that much difficult to learn. So once if you know what is convolution operation and how all these things are working and how all these things are interacting together, then studying object detection or segmentation architectures are not going to be that much difficult, except for classification task, we have a different loss function. For detection tasks, say for example, you may have cross entropy as your loss function. For detection task, we must have a different loss function, probably let us say focal loss, okay, because this is a different scenario. For segmentation, again, we will have a different loss function. Okay, so only there will be a change in loss functions. Other than that, there will be additional components other than this convolution layer and max pooling layer. Okay, so there will be some sort of additional components. So usually this is the first attempt to use deep learning architecture for object detection. Okay, so that is RCNN, Regein CNN, and then Foster RCNN. Today, usually people will pick up YOLO. You only look at once architecture for object detection bar classification. So it must be object detection bar classification. Okay, so first you localize where the object is, and then you classify what the object is. Okay, so this is the difference between the object detector and the object classifier. So here you can see my input image contains only one object. Okay, therefore classifier outputs only one label. Now my input image contains two objects with the bounding box. Okay, then the object detector gives you the output from the object detector is the object detector is label and as well as the bounding box. So as you can see from here, this bounding box carries an information about the coordinate, right? So this, as you can see from here, this 20, 30, all these things are actually the coordinate of this bounding box. Okay, then you can draw the bounding box on the detected object with the respective label. You can do all these things with OpenCV. Okay, so if you are building an application, especially in computer vision, then the better library that comes up with all sort of functionalities required to carry out any sort of computer vision task is OpenCV. Okay, so now you can merge this, you can develop deep learning model in PyTorch or anything, then you can deploy this deep learning model into OpenCV as well. Okay, so by the way, so this is a difference between object detection and classification. The one thing that you have to remember is that object detector doesn't care about what is there inside this detection. Okay, so say here you can see the first stage of the object detector. Okay, it says there is some sort of objects probably inside this particular region. So that is why it is called as region proposal. So it will look for some around 2000 regions. Okay, then it will just put the bounding box on those regions and tells that there may be some object inside this region, but it doesn't know what object it is. Okay, so it gives you just the bounding box coordinate, and then you can take intersection over union. Okay, to merge all these bounding box and to just stick with one, because this bounding box and this particular bounding box both points to the same object. Okay, then you can overlap these two bounding boxes and then just rectify it. So once an object is detected or localized, okay, I found the bounding boxes in, if I have a huge image, then the object detector returns the bounding box. Okay, it doesn't show what is there inside this bounding box. Then you have to use a classifier. Okay, so this is how the first deep learning architecture had been used to find the object and classify it. Okay, so object detector followed by a classifier. Okay, but this is extremely slow because you have to create a window, and then you have to move that window across the entire image, and then you have to check whether this contains an object or not. Once doing so, then you have to carry out the classification. Okay, so when people have overcome all these problems, and finally they end up with a YOLO model. Okay, so as of now, as I think YOLO is the state-of-the-art model used for object detection. Okay, and not YOLO object detection is not suitable for all applications, so it works fine with natural images. Okay, so recently I have just gone through a paper where detecting. So if you have a newspaper, you might see some sort of graphs in the newspapers, right? So researchers from IIT Madras have developed their own object detection architecture suitable to recognize the objects, I mean the bounding box of these graphs. Okay, so I don't know the exact name, but you can search for it. Okay, because none of the object detector works well on this kind of object detection task, which means recognizing the graph and the box on the graph on a paper, right? So it is quite involved and it is very difficult. So they have considered this problem for their research, and then they have just overcome this problem by developing a new architecture. So there is always a scope for an improvement. So finally, the third important application in computer vision, the third important research problem in computer vision is image segmentation. So image segmentation is quite different from image classification in terms of the process as well as in terms of the architecture. Okay, so what is the difference between detection and segmentation? So I have an image, I pass this image to a classification algorithm, and I also pass this image to a segmentation algorithm. So the classification algorithm only gives me the label, right? So it will say what this image is. It will just return the class label, right? So it will say probably it is a bicycle or probably it is a person, like this. Okay, so it is going to be just a number. That is what I wish to highlight here. It is going to be single number, or if it is one hot encoder, it could be if it contains 10 classes, it will be 10 numbers, probability of all those 10 classes. But segmentation algorithm, my input is an image, the output is also an image. Okay, so this is a different scenario compared to the previous case. So here you can see whatever the size of the input, say for example, if the input size is 60 cross 100 cross 60, okay, then the output from the segmentation algorithm should also be 100 cross 60. Okay, so this is entirely different thing. So therefore the architecture will also be different. Okay, so coincidentally, or surprisingly, segmentation, the first deep learning architecture for segmentation task has been actually developed for medical image segmentation. But later, that same concept has been used for all sort of segmentation, even in autonomous vehicle, detecting the bounding area of an object in an image is very important task. So in autonomous driving vehicle, even in they deploy this segmentation algorithm. Okay, so here you can see the output of the segmentation algorithm. So there are two types. One is dense prediction and another one is semantic. So what is mean by semantic? The word semantic means is simply the structure. Okay, so all of them are persons. So again, it is a type of classification extended to pixels. Okay, so what this segmentation algorithm does is that, so I have three classes, actually two. One is person and another one is bicycle. The third one is a background. So it could be anything, sky or a road, or it doesn't matter. Other than these two, person or bicycle, everything is considered as a background. Okay, so you can think of this segmentation algorithm is doing classification on each pixel. It will take this pixel and then it classify whether this particular pixel belongs to a background or bicycle or a person. So it has to classify it. So based on this, it will give the color. Okay, so if it is black means it belongs to background. Suppose if I take this pixel, then this pixel belongs to bicycle. So it differentiated with color. Sorry, person. Similarly, this pixel belongs to person. Okay, so if you do pixel wise classification, you know it will take enormous amount of computation, because even if it is size of the image is very small, 100 cross 100, then I will have this 10,000 numbers, 10,000 pixels, right? And into 3, because it is a color image. So there are 30,000 pixels. So I have to classify all these 30,000 pixels into three classes, person, bicycle, or background. So it is computationally expensive. Even though it gives a good output, it is computationally expensive. So here all these three persons are considered as a person. So it is called as semantic. But if you distinguish one person from the other person, even though they belong to the same class person, but these two are different person, means we call this as an instant segmentation. Okay, so all of them are person, but they are different. So they just differentiate it with color. Okay. By the way, whatever the segmentation task you are given with, we will use an architecture called as unit architecture. Okay, so here I am just put all the outputs in a single slide so that you can see what is the difference between deduction, segmentation, and instant segmentation. Okay, so one of the important architecture used for image segmentation is fully convolutional neural network. Okay, so the name fully suggests that in a CNN architecture used for classification purpose, I have two layers, right? So one is convolution layers. I may have some 7 convolution layers. So finally, I will flatten the output from this convolution layer, and then I pass it through fully connected layer. So it is a traditional artificial neural network used for classification purpose. Okay, then it will give some numbers as an output. But here, the word fully actually reflects that I have two parts. One is an encoding part, then another one is a decoding part. And since my input is an image, my output also should be an image. If I use CNN here, then instead of using fully connected layer, in the decoder part also we are using CNN. Okay, then the output is going to be an image. So that is why it is called as fully convolutional neural network. There is no artificial neural network in between. So it is completely covered by fully convolutional neural network. Okay, so as you can see, these segmentation algorithms are actually being deployed in autonomous driving vehicles, because knowing the exact boundary between two objects is critical during driving. So you could have deployed object deduction architectures as well, but it will not give you an exact boundary. Only the segmentation algorithm can give the exact boundary between objects. Okay, even you can calculate the area, you can calculate the size of an object, If it is a medical image segmentation, if you want to calculate the spread of the tumor or size of the tumor exactly, then you have to go for segmentation, not for detection, not for classification. Okay. Even in remote sensing, you can use this to calculate cultivation area, all these things. Okay. So segmentation plays or occupies more number of real world application than classification. Okay. So one architecture that is commonly used for all type of segmentation algorithm is U-Net. So the network is called as U-Net because of its U shape. Okay, so you can think of this network is composed of two parts. One is an encoder part and another one is a decoder part. Okay, all the layers in this architecture is composed of only convolution operation. Okay, so every layer is carried out some sort of convolution operation. So this last layer, okay, this layer is called as bottleneck because of its resemblance to the bottle. Okay, so this is quite interesting architecture. So the encoder part is what we have discussed earlier. Okay, so you can see it is a convolution layer, max pooling layer. So every component is contains convolution layer and then max pooling layer. But if you look at the decoder part, again it is composed of convolution layer, but there is new word called as up convolution. Okay, so either you call it as an up convolution or upsampling, okay, or transposed convolution. So all of them are mean to same thing. Okay. Okay. So the reason here I have some set of numbers. I have an output. Okay, so output from the encoder is 16 cross 16 cross 512. But what is the output expected from this architecture? This is 256 cross 256 cross 1. So I have an image of size 16 cross 16 at the encoder output, but I need to upsample this image to have size of 256 cross 256. Okay, so we need to accomplish this task. Okay, so there you cannot use simple upsampling procedure simply by repeating columns and rows twice or thrice or 10 times. So it will reduce or it will show you a checkerboard effect, right? It will not look good. So you are making this process a learnable process. Okay, so for that you are using this upconvolution. So the mathematics behind this is again quite involved. How this upconvolution, upsampling process is costed as a learning problem. Okay, so I think if I talk about this, it might confuse you. So let me keep this with me. If I have time after showing a demo, then probably I will talk about this transposed convolution. Okay, so as I told you already, there are plenty of resources available in the internet, right? So there is no what to say in today's era. If you have an interest, if you have a curiosity, there are trillions of resources available in your fingertip. Okay, so only the Google is the medium where you just type it, it will bring it. Okay, so the only thing is we have to learn the fundamentals thoroughly. Okay, whether it is about coding or about mathematics or whatsoever. So whatever the fundamentals required to understand a particular architecture or particular application, we have to learn it thoroughly. So once if you learn the fundamentals thoroughly, then we can code it. Because even if I use PyTorch, there are plenty of tutorials. Okay, many people are writing pages and pages of tutorials, but all of them are assuming that, okay, so if you refer all those tutorials in different blog or in a PyTorch own documentation, they assume you have satisfied the fundamentals. Okay, so you know the fundamentals of the deep learning concepts, fundamental max concept. Also, you know the fundamental programming. You have the fundamental programming knowledge in Python. Okay, so especially you should have a good knowledge in Python, especially in OOPS concept and using this generator concept, all these things. So once if you learn all these things, approximately it takes 2 years. Okay, so if you are completely new to this field, if you have no exposure to Python, you are working in MATLAB means you can learn Python in 1 month. It is not a big deal. But if you are completely new to deep learning, it will take around some 2 years to, or I may say 1 year if you are consistently working on it. Okay, to learn the fundas. So once if you know all these things, then there are plenty of tutorial. Once if you go through the tutorial, since you already know the fundamental requirements and you have sufficient coding knowledge, you can understand their code and modify it. It is not going to be a big deal. Okay, so here I am just listed out few references. So I will share this slide. You can refer this article to know more about transposed convolution. Okay, it is a quite an interesting article, so I would recommend you to read this article, okay, if you have a time. So with this, let me close this session. And if you have doubts, you can ask. So we will have a live coding demo session or hands-on session during the afternoon. Okay, so if there are no doubts, then I think we may wind up the session, ma'am.
Hope participants have any doubts there. On behalf of myself and all the participants, I thank Arun Prakash for providing the essential knowledge in the deep learning models for computer vision. Thank you, sir.
Thank you, ma'am.
The feedback link is posted in the chat window. All are requested to fill the feedback form.
Ma'am, the link is okay. Now,
The next session starts at 2 p.m. Thank you all.
okay, ma'am.